I am very happy to introduce our second speaker this morning, Rahul Mazumder, Associate Professor in the Operations Research Center of MIT's Sloan School of Management. Rahul will be speaking about predictive and prescriptive analytics at scale. So please join me in welcoming Rahul.
Okay, thank you. Thank you, Eric, for the introduction. Thanks for the invitation, and thanks to all of you for being here. So I'll be talking about predictive and prescriptive analytics at scale. So these are two key components of an analytics pipeline. And at the beginning, I'd like to provide a few acknowledgements and references. So I'll be touching upon three recent papers that I've been involved in. The first two papers are on machine learning algorithms, which discuss more on the predictive part of analytics. And the third part is how do you use the outputs from these machine learning methods and feed them into large-scale decision-making problems. In particular, in a recent work with collaborators at LinkedIn, we designed specialized solvers to solve linear programming problems arising in decision making or prescriptive problems of involving decision variables, number of decision variables up to a trillion scale. So these are, to our knowledge, these are the largest scale instances of linear programming problems that have been deployed on real data sets. So this work involves research that I've been done with my collaborators at MIT, members of my research group, as well as people from Google Research, as well as people from LinkedIn AI. So let me give you an overview of the predictive and prescriptive analytics components and what I actually mean by it, and how I'll be discussing these two components in the context of my talk. So let's start with a few examples that we are all familiar with. So let's think about the problem of email volume optimization or notification optimization. So as a platform may want to optimize the delivery of emails or notification to users. This can be done for marketing purposes. This can be done, for example, to gain user attention or to bring users back to the platform. Now, in this case, a predictive component of the problem may be learn based on historical data how a user is going to respond to different notifications or emails that have been sent to it, to the person. This depends upon the email content, the way in which the text is structured, so on and so forth. Based on the historical data, a machine learning algorithm is going to try and learn what the conversion rate can be. The second part of the problem, which is also a very important part of the problem, that is the decision-making component or the prescriptive part. Over here, a platform may be interested in optimally allocating notifications subject to certain budget or resource constraints. So for example, we don't want to overwhelm users with thousands of emails because that may be bad from a platform viewpoint in terms of user engagement. Talking about problems in matching, these problems arise a lot in e-commerce platforms. In the context of social networking or recommendation sites, the matching problems also arise. For example, ranking news items to users, friend recommendations, or network growing, and so on and so forth. We can also think about matching drivers to riders in ride-sharing apps. So at a very high level, these problems involve one part, which is a demand estimation part or a value learning component, that is learning the value of an engagement in a network if it were to happen or if it were to materialize. This is the machine learning part. And the second part is the decision-making component, where we take the output of the predictive component of the problem and feed it into a large-scale decision-making problem. And these two things form an important part of the analytics platform. I'm not saying these are the only two parts. Of course, data collection and understanding the business context are also very, very important. But these are two components that I'll be focusing on in my talk. All right, so to make things concrete, let's talk about a motivating example, that of friend or network or friend or connection matching problem. So let's throw in a few alphabets over here. Let's define what is known as a user value. So P1 is a value model or an engagement model. So I is an user. So think about people, viewers on a networking platform. When a user goes into a networking platform, then the platform is going to show a candidate of users who the viewer may think about connecting with. So P is a value model. This basically describes the value of showing a user J to a user I. And Xij can be thought of a decision variable where which captures the probability of showing a user J to a user I. Now, I've just written the weighted sum. Of course, there is some optimization that we want to do. First of all, PIJs, as I said, is going to be the output of an machine learning problem, which is going to be done based on historical data. Now, once that is given to us, we want to maximize, for example, user value. In that case, the decision variable is going to be these Xijs. That is, which of the users, so when a user comes into the system, a viewer comes into the system, which other users should I be recommending to the user? Okay, so that's the decision that is being taken by the Xijs. Now, of course, we don't want to maximize this in an unconstrained fashion. There are going to be business-specific constraints as well. So for example, there can be constraints such as the total invites sent is greater than a certain threshold. So these thresholds are user defined numbers, depends upon the business context. We can also choose to limit the number of invitations every member for every member in order to prevent overwhelming of members. There can be several other constraints depending upon cohort-specific constraints and so on and so forth. There are going to be additional constraints because these decision variables are going to lie in a probability. So the predictive analytics part, which is going to focus on building ML models for learning the value model as well as the invitation model. So this looks at historical data and then is going to crank out numbers for P1s and P2s. The prescriptive analytics part of the problem is going to take this as a starting point, and then it's going to solve this problem to learn the decisions. Now, there is going to be a big simplification that I'll make over here, though, I mean, so if you, I would encourage you to look at our paper where this is actually used in an online fashion, offline and online optimization. But for the purposes of this talk, I will separate out these two problems. I'll first talk about the predictive analytics part, and then I'll talk about the prescriptive analytics part. But usually we would like to solve them in conjunction. There is going to be there are two problems that are tightly coupled together. All right, so talking about the scale of the decision-making problem, this was kind of interesting because when I was working with my collaborators at LinkedIn, I learned that many of these linear programming problems arise quite naturally in a wide variety of web applications. But it appears as if, at least based on the published literature, some of the methods that are commonly used are kind of ad hoc methods because it's not possible to solve these optimization problems at such gigantic scales. So these are simple problems, simple looking problems. In particular, they're linear programming problems, but they're very difficult to scale at many large instances. So by scale, I mean the number of viewers can be of the order of 10 to the power 8. And the number of users that may be recommended is of the order of tens of thousands, and we are dealing with 1 trillion decision variables. So let me talk a little bit about the predictive analytics part. Now, for the purposes of this talk, I will be focusing on one classic predictive algorithm method, and that is the boosting method, gradient boosting machines. So GBM, gradient boosting machines, loosely speaking, combines several weak learners into a powerful ensemble. And this powerful ensemble to many people is also known as an additive model. It has garnered a lot of attention across the computer science as well as the statistics communities. And over the years, we have gradually understood from a methodological viewpoint what this boosting does. It's extremely popular and works quite well in practice. In terms of interpretability as well as hyperparameter tuning, it works pretty well. It is often used in production models in several organizations. And it is very good for unstructured data. It is also very good for handling heterogeneous data sets, for handling data sets with missing values, outliers, and so on and so forth. Anyway, there is a long literature on this. There is a long line of research has been done on this, and several open source implementations are also available. One of the curious things of boosting is that it imparts algorithmic regularization. So even though I would like to say we understand this very well, there are many things that we don't really understand about this problem at a very deep level. And these things actually keep coming up in understanding overfitting aspects of neural networks and so on and so forth in a very different context and a very different guise. But even in the context of gradient boosting machines, some of these aspects are not very well understood. In this talk, I'll talk about addressing some of the key outstanding computational challenges. I'll illustrate how it appears, and then it's actually a very simple thing. We can see clearly why this computational scalability challenges arise, and I'll talk about algorithms which can actually help mitigate that. So this work is based on a paper that we wrote. It's called Randomized Gradient Boosted Machines. So it adds a layer of randomization on top of the usual gradient boosting machines. There is a version of randomized gradient boosting machine which is known as stochastic gradient boosting, but this version is, but the current version that I'm talking about is of a very different style and spirit. So in order to understand our proposed new algorithms, I'll give you a brief overview of the setup that helps us understand this algorithm. So we have data, yi's and xi's. Y is the response and xi's are the features. To make things simple, I will say that we are dealing with a least squares loss function. There are n samples. And we are minimizing a loss function over a certain so-called function space. This function space can be defined in terms of linear models. It can be in terms of neural networks. And I'll focus mainly on tree-based methods. So gradient boosted machines, it leads to an ensemble, which is basically a linear combination of trees. So these are going to be the weak learners, and we add them up and then form an ensemble. There are two components over here. One of them is the learning rate or the step size, and the other part is a weak learner, which are these trees. Now, interestingly, the sequence beta m and these b tau m that are the weak learners, these are actually chosen sequentially by gradient boosted machines. And together, they control what is going to happen to the training error and what is going to happen to the test error. In other words, they control both the data fidelity and regularization aspects and help us understand overfitting aspects of this algorithm as it evolves over time. So to set the stage, let's revisit the classic gradient boosted algorithm due to Friedman in early 2000s. So the algorithm works as follows. It starts with an initialization. F naught of x is the null model, and it performs the following steps in a sequence. It calculates the residuals, and then it tries to find out the best weak learner, and then it updates the model. Now, this is the very basic version of gradient boosted machines. All right, and then even if I look at the gradient, this algorithm, you will see that there is immediately an object that stands out as being computationally intensive, and this is this part. So we are trying to find out a good tree or a weak learner among a huge collection of possibilities, which can be of exponential growth. So the question is, how do we actually decrease this complexity from exponential to something else? So I considered over here trees of depth D. So the way in which usually trees work, they do it greedily. But even if you're thinking about training a tree of a shallow depth, there are many possible splits to select from, and that leads to huge runtime complexity increases. So we need a way to address this. And here is an algorithm that we proposed, which is known as randomized gradient boosted machines. It's actually a very simple algorithm, but it works surprisingly well, and it has been and it has the potential of being used in many other contexts. For example, we have used this algorithm in solving other types of problems which are totally unrelated to boosting. So it's interesting. So how the algorithm works, it's actually a simple method. So let's start with the greedy method. So we want to find out the minimum of potentially a large collection of numbers. Instead, what we do is, instead of finding out the minimum from this large collection of numbers, we take a random subset of these numbers. So we take a random subset j of tau, and then we find out the minimum of this. So in a nutshell, what is happening is gradient boosted machines are slow because it does a huge search over potentially many possible trees. It searches over splits like crazy. Now, what this proposal is basically telling us to do is, instead of searching over that, quantize them in a certain fashion, or take a random subset of quantization. And then once you quantize them or reduce the cardinality of that set, then actually choose greedily from that reduced set of numbers. This leads to big runtime reductions. And this random selection rule that I discussed, this can also be tree structured, depends upon the structure of the tree. So by the way, for those of you who are very familiar with XGBoost or popular boosting machines, you'll see that XGBoost actually implements some of these heuristics already in their algorithm, which actually leads to pretty fast runtime performances. However, many of these algorithms are not understood from a principled viewpoint. And this work actually tries to quantify some of those aspects. So we also discuss some theoretical properties of the gradient boosted machines. All right, so let's to give some intuition, let's talk about how this works actually in practice. So this is a real data set, a classification data set, and we are looking at two panels over here: runtime along the x-axis, and then we are looking at the testing loss in this panel and the training loss in this panel. So GBM, the traditional version of GBM, which does a brute force search across all possible weak learners, this actually evolves pretty slowly. So it actually is quite slow in terms of getting a model with good test error. On the other hand, if you look at all these candidates over here, that is a randomized counterparts of gradient boosted machines, these actually work pretty well in terms of leading to a model with good training error as well as a good testing error, and it does so in running in a much shorter amount of time. So randomized GBM actually does lead to significant reductions in computation time. And potentially, if you think about the algorithm that I proposed, that I just outlined, you have a huge possibility of numbers. And from that, you're taking us just from a small subset of it and then choosing greedily from that. So it has implications for scaling up some of these problems to enormous scale instances. The other useful thing, which is actually very intriguing, is this randomization also is useful from a regularization perspective. That is, in terms of out of sample or generalization performance, it actually imparts useful regularization. This is one of the unwanted consequences of an algorithm like boosting, but it is actually one of the most useful reasons why boosting is used in practice. So I'd like to switch gears slightly, and then I'll talk about how can we use two pillars of machine learning algorithms. One of them is decision trees, and the other one is neural networks. How can we integrate the benefits of trees and neural networks? I mean, clearly they do different things, and they are also extremely important in their own right. Is there a way to integrate them in a suitable fashion? So this is the topic of this paper that I'll give an overview on. And this paper is being presented at ICML currently as we speak, actually. And this, in a sense, it integrates some of the computational and statistical aspects of desirable properties of trees, as well as the rich feature extraction capabilities of neural networks, and puts them together. So this paper actually starts to investigate a key area in the context of large-scale training, which combines neural networks as well as trees, and this is the notion of conditional computing. What is conditional computing? So in a nutshell, it's not very formally defined, the notion of conditional computing, but it is actually easy to understand from a picture. So over here, I have a tree. So there is a sample that is being routed, and it takes a particular path. So if I look at this sample that is being routed, it is being routed across a very specific path. That is, this sample does not touch the other nodes or leaves of the tree. On the other hand, if I look at a neural network, these edges or links are scattered all throughout the network. So this is a notion of dense computation, and this is a notion of conditional computation. So this is one of the good things about trees, the notion of conditional computation, and this can actually help in parsimony. And this has very useful consequences in terms of building scalable algorithms, which combines neural networks and trees. And of course, as we all know, trees are good in terms of parameter tuning, as well as they have nice interpretability constraints. And neural nets are extremely good in terms of feature representation. So our proposal is what we call TEL, the tree ensemble layer, and it proposes to hybridize these two methods together. This TEL actually acts as a layer. And as a matter of fact, you can take your favorite layers in neural networks and put the TEL layer in any particular part of the neural network that you would like. Now, in order to make joint end-to-end training possible, in order to make that training possible, we need new algorithmic ideas. As a matter of fact, the boosting ideas that I just discussed, the traditional gradient boosted machines, the stage-wise optimization ideas, they do not work over here. You need something which is joint end-to-end training based methods based on continuous optimization stuff. And that's the reason why. So we designed some algorithms which can actually do this. And this is done by end-to-end training via stochastic gradient descent. And there is a very specialized custom backpropagation that is also inbuilt. And this can also be extremely effective. All right. So in case you're interested, there is an open source implementation of this in TensorFlow as well as in Keras. And this is hosted on the Google Research website, GitHub repository. And it is known as Tensor TF trees. And in a nutshell, I'd like to highlight what do we actually gain if we use tree ensemble layers in the context along with a neural network. So we gain mainly in terms of model compactness and robustness. All right, so what does model compactness mean? So basically, let's illustrate this in the context of decision trees. So we have three different training instances, real data sets. The number of trees are on the x-axis, and we see that there are two competing candidates. One of them is TEL, that is a method that I discussed, combining neural networks with trees. And the other one is the classic gradient boosted trees. So what we see is you get a very, very high accuracy with a much, much smaller number of trees. Okay, so you get a much more parsimonious model if you combine TEL within a neural network. However, you don't lose in terms of accuracy. As a matter of fact, the accuracies in some cases can improve, and in most of the cases that we tried, even in the context of CNNs in computer vision applications, these lead to actually very competitive performance. But there can be significant boosts in terms of model compactness. So with this, I'd like to basically give an overview. What we have discussed are two key methods of boosting. So we usually think the gradient boosted machines, these are old methods, everything has been solved. I'd like to argue there are many things that are still not understood about this, and research is going on. We are building newer and newer algorithms, and especially when we try connecting the best of both worlds, like neural networks and trees, then we get models that seem to be extremely competitive and have the potential of being being used as state-of-the-art algorithms in several other applications. All right, so in the remaining amount of time, I'd like to switch gears and talk about the prescriptive analytics part of the problem. So again, what we'll be doing is let's go back to the motivating example that I spoke about, the friend or connection matching problem. So we set up the problem in the following fashion. We want to maximize user some value of engagement subject to a bunch of constraints. Now, initially, when I introduce the problem, I say that these PIJs and T2s, these are going to be the output of some ML model. Now, these can be the outputs of gradient boosted trees. It can be an ensemble method. You can use neural networks. You can use anything. This is the nice thing about modularity, because in a certain business context, you may like or have an affinity towards certain machine learning models. You take these as an input, and then this decision making problem is going to adapt to those as the inputs. All right. So the key challenge that we addressed in this problem with researchers at LinkedIn AI is, how do we solve these problems at extreme scale? And by extreme scale, I mean the number of users are of the order of hundreds of millions, and the number of potential recommendation list items is of the order of tens of thousands, and we are dealing with potentially 1 trillion decision variables. All right. So now, so let me give you a brief overview of how the algorithm actually works. So a key way to actually make this method scale is an exploitation of what we know as problem structure. Okay, so this problem structure is hidden in this problem. Actually, these large scale web application problems. Some people say that this is a restricted class of problems, but I would argue, as will my collaborators, that many of these problems arising in web applications have. I'm not saying all of them, but many of them have this structure. And if it has this structure, let's exploit it to build better algorithms. So this constraint matrix A has two components to it. One of them is a global constraints, for example, the cohort level constraints or total invite constraints. And it also has this other block, which, for example, describes constraints in terms of item level constraints and limits on invitation per user. We decouple this problem by encoding these probability constraints in specialized polyhedral sets. And let me give you a key insight as to how this method works. What makes this algorithm scale at unprecedented scales? So the key insight is actually surprisingly simple. It basically makes the following observation, that in many of these problems, the number of rows of A is actually very small. Okay, so remind you, the number of columns of A can be of the potentially of the order of trillions. But the number of rows of A is of the order of at most thousands or tens of thousands. Okay, if the problem is of that form, then this method is going to be applicable or efficient. Otherwise, this method is probably not going to be as efficient. You need other algorithms to try it out, or probably give up hope. We don't know how to solve it currently. So the other part is decoupling the A's and the C's. So I'll not have much time to talk about how the algorithm works, so I'll quickly move over this. So basically, we use an old idea from optimization, and it basically says we have the LP. Instead of solving the LP, let's solve a perturbed version of the LP. And then when we solve the perturbed version of the LP, looking at the perturbed version of the LP, we are actually dualizing it, and then the dual is smooth. And when we are calculating the gradients, the key insight that we use is that the gradient admits a distributed computation. So this is a problem. This distributed matrix vector multiplication has been implemented with serious amount of coding, and I don't have time to talk about the details, but the details are going to be in the paper if you are interested. But I like to wrap it up by talking about how it actually works, how this method can solve problems of unprecedented scales on proprietary data. So this is a test on a large-scale volume optimization problem as well as a matching problem. So we look at both volume optimization problems and matching problems. We go up to problem sizes up to 1 trillion variables. And then if you're looking at the time taken to run this algorithm, Eclipse, which is our proposed algorithm, can solve a problem with 1 trillion variables in under 12 hours. SCS is actually a very good open source solver. And there is a distributed implementation of SCS that my collaborators created, and SCS is unable to solve problems of this scale. And we have seen in several other metric, we have compared this method with other types of heuristic, like divide and conquer methods that are often used. And this optimization method seems to have an edge, as it is discussed in the paper. All right, so let me conclude. So we can consider two components, two key components in an analytics platform. One of them is the predictive part, and the other one is a prescriptive part. The predictive part focuses on boosting and proposes an algorithm to scale up boosting even further, known as randomized gradient boosting. And there is this close cousin of this, which is basically combining decision trees, the power of decision trees with neural networks. And this layer that we propose, which is TEL, it can be used inside any of as a neural network layer. The prescriptive part, which is done as a follow-up part of the predictive part, which allows us to solve decision-making problems or LPs, which arise in pretty large-scale instances. Now, of course, I mean, this is just the beginning. There are many different opportunities. There are many other problems that might benefit from an analysis using predictive as well as prescriptive lenses. And we believe some of the methods that we have been investigating, they will lay the foundations of tackling more serious and more interesting, challenging problems that arise in several other business applications or in other application domains. Thank you.
Excellent. Thank you so much, Rahul. Quite a number of questions to get through, and so I'm going to do exactly what I did on the last pass and combine a number of these. You mentioned in the earlier part of your talk, as you were talking about gradient boosted machines, that there are areas where the technology works, but we don't necessarily have a perfect understanding of how the technology is working to solve the problem. Could you talk for a little bit about the challenges or potentially the opportunities that this presents, and how we might be advancing our research to understand in detail how we're solving some of these problems?
A good question, actually. So, all right. So let's go back to the gradient boosted. So, okay. So there are many. Okay. So let's go back to my slides. Yeah. So I mean, so boosting has a long literature. So one of the key parts about boosting, which is still a mystery, is how does it impart regularization? So if we talk about some of the classic methods, age-old methods like ridge regression or lasso or subset selection and methods like that, or even decision trees, I would say, if you solve the decision trees optimally, there is a loss function that we have, and then there is a penalty function that we have, which basically penalizes the complexity of the model. Now, once you have a problem of that form, then there is rich theory, which they basically tells us what is going to be the generalization properties of that problem. However, boosting is not of that form. Boosting is basically an algorithm. It's a very nice algorithm, but it's an algorithm. It runs, it makes several iterations towards, and it progresses towards minimizing training error. And then also it has good useful implications for out of sample properties. So exactly quantifying the behavior of that is one of the challenges. And this is even more interesting because we see this behavior of boosting, that boosting doesn't overfit. For example, even if you go on, let it run for hours and hours and hours, the training error is literally zero, but the testing error doesn't go up. So why does this happen? We are seeing this also in the context of neural networks. So some of these aspects are not very well understood. Of course, there is a exciting research which is going on trying to understand this in the context of neural networks as well as in boosting, but there are many aspects that remain to be addressed. The other part is about the computational challenge. That is, when you actually try to train a tree, right? So the usual version of the gradient boosted machine trees, you're trying to find out, you're looking at the residuals and you're trying to find out the best tree fit to it. But it's actually an exponential search complexity. So what do we do? So XGBoost actually, and some other algorithms actually use some very clever heuristics. What they say is, okay, suppose I have 1 million samples and I'm trying to split on a particular feature. There are 1 million levels. They use these quantization of the different values based on quantiles of the function, and then based on that, they sort. They try to decide a split, which is actually a very good method. But then the question is, can you actually even use these algorithms to improve upon the complexity of those methods? And this research that we have been doing along these lines, they have the potential of answering some of these questions. As a matter of fact, I didn't talk about some of the follow-up work. There has been very interesting follow-up work by my co-author and researchers at Google, where they're proposing accelerated gradient boosted machine versions, where how to even speed this up. There is also another follow-up interesting work on how to use boosting ideas, again coming up from Google, where they discuss how do you think about these ideas and add additional concrete regularization to improve performances of these methods. So there are many of these interesting algorithmic challenges, as well as these which are directly being informed by our understanding of this. And you may ask, what is actually making this possible? I would say a new lens to address this. So we are investigating this problem by using new developments in optimization. And some of these developments in optimization are pretty recent. And as we are understanding optimization algorithms better, this has a direct consequence on how we understand boosting algorithms better. So I think there are exciting opportunities over here.
Yeah, so really a case of the research moving hand in hand with technological improvement.
Absolutely.
And enabling yet more of the same. Excellent. You touched on this briefly when you were introducing TELS. Can you talk to us a little bit about explainability and how it relates to trees versus neural networks, how TELS might influence that, and how randomized gradient boosted machines might make that mix a little bit more complex still?
It's a very good question. So all right, so there are many components to that part. All right, so let's talk about one part, right? The gradient boosted machines. So gradient boosted machines, how is that going to help us improve interpretability? All right, so my premise is we like trees. Okay, some form of trees, as long as they are not too deep, they are interpretable. If we add a bunch of trees, as long as we don't add super large number of trees, they are still interpretable. Okay, now that's the context of gradient boosted machines. Now, what randomized gradient boosted machines, so again, so what are the components? One of them is adding a few number of trees. So there is a notion of parsimony. There is a notion of sparsity. I am not going to add too many trees. So gradient boosted machines is actually pretty good at that. Randomized gradient boosted machines tries to mimic that notion of sparsity. It can lose out a little bit in terms of sparsity, but not by much. However, you can make these methods much more sparse. That is, you can have a gradient boosted machine which is with better predictive accuracy with much fewer trees, and that's the place where joint optimization comes in, and TEL can actually do it pretty efficiently. So this is one of the ways to think about TEL. That is, it is training an ensemble of trees. Okay, so in particular, you can think about TEL is doing it. It is getting much richer representations because it's borrowing rich representations from neural networks. However, when you add these guys together, you add a bunch of trees together and you jointly optimize. This joint optimization, as opposed to a greedy optimization, leads to superior parsimony properties. It leads to more compactness. And that's the reason why we believe that TEL actually leads to much more compact models compared to usual gradient boosted decision trees. That's one, because of the joint training. And the other one, which is also very important, is it leverages rich feature representations from neural networks, which also has a bearing. And the other point, which is also extremely important, that is the notion of conditional computing. That is, a sample, when it is routed through a network, it is actually touching a small subset of the nodes, as opposed to touching all the nodes as in a dense computation in the context of neural networks. Because of this, you can actually design custom backpropagation methods which exploit sparsity extremely efficiently. And and we have seen that in several of the examples that we have tried so far, TEL actually encourages much more sparse models, and it does so without sacrificing on predictive accuracy. And there are other details as well, which actually makes this joint optimization possible, because it's not a greedy learning method. It's a joint training method, which is being done by SGD. So there are many different components which are brought together to actually make this more parsimonious and compact.
Excellent. And as a follow-up on TEL, we've seen suggestions that trees can be much more efficient, particularly for computation at the edge, than
Absolutely.
neural networks.
Yes.
How do TELs fit into that landscape?
Excellent question. That's an excellent question. And as a matter of fact, that was the starting point of this, one of the motivating aspects of this. So trees are excellent in terms of computation, allows for fast, efficient, parallelizable inference. Neural networks, okay, are okay. To some neural networks are slow comparatively. So TEL is somewhere in between. Okay, so it tries to leverage the speed of decision trees because it capitalizes on what makes decision trees fast. I would say mainly conditional computing. And but then again, it tries to leverage the richness of feature representation of neural networks. So I would say TEL is somewhere in the middle of them.
Excellent. Thank you very much. And while there are a couple of more questions, unfortunately, we're out of time. So I would encourage anyone that has additional questions for you to reach out directly. Thank you so much, Rahul. It was great to see this work and really very excited about the possibilities of it.
Thank you.